Good morning everyone. Welcome to the new series on IBDP curriculum for physics. So this is the chapter on relativity. As yesterday I had already told you that we will be starting a new chapter. So totally there will be 5 different videos only on relativity chapter, and after that I think I'll be putting across the different problems based on relativity. Okay, now let us begin with this. Let me share my screen to show you like what we are going to do further. Okay, so the first thing to learn about is the reference frames, the inertial and non-inertial reference frames, and the Galilean transformations. In this video, we are going to look into this. Okay, so what is a reference frame? For example, I have shown you here about what is a reference frame. The reference frame shows you something like you have a particle which is now revolving around it, okay, in a circle. And there's one more particle which, according to this yellow particle, is moving in a straight line. But if you look at it from the rotating frame of reference, the stationary observer, the red particle appears to be moving in a straight line, while with respect to a rotating frame, it observes that it is being seen to be in a rotating frame. So therefore, based on the frames of the references, we can say whether a particle is moving in a straight line or it is moving in something like a rotating frame. Let us take up one more example to see this. Now shown here is something like a particle which is moving in a circular frame, okay, and the mapping of this particle which is seen as a shadow on a one-dimensional line over here. So what is this? For example, this is nothing but your SHM, which you already learned. So here also the particle, red particle, according to the observer who is, suppose the reference frame is fixed at the center of the circle, it appears that it's moving in a circle. On the other hand, if you map the same thing onto a straight line, it appears that it is appearing like it's moving like a vibratory motion, right? Now let us look at some more examples to understand this. Now what does this tell you? This tells you something about a monkey which has been falling off from the tree and it aims at a banana, and this banana for the monkey appears to be coming in a straight line. While on the other hand, if you look at the point of the observation from the launcher, okay, you look at the launcher there, and you see that as the banana has been thrown, it describes something like a projectile motion because of the gravity. So therefore, now both the motions are same, but unfortunately, it again depends upon who is the observer over here. Let us look at one more example. Okay, so for example, you have something like a person standing on a cart which is being moving across, and then you throw a ball. Okay, according to the person in the cart, when he's throwing the ball upwards, it appears to him it's coming in a straight line downwards to him. But for an observer standing on the ground, it appears that the ball appears to be moving something like a projectile motion, right? So therefore, it all depends upon what kind of reference frame are we looking into. Are we in a stationary reference frame? Are we in a moving reference frame? So therefore, the trajectory of the particle will differ. Maybe sometimes the velocity will differ, and so on. Okay, let us look to the final one. So this is a very obvious one which we actually see it over in every day-to-day life applications, wherein let us say, for example, you are standing on the left-hand side of the road and you are able to see that a car is approaching you in this way. When a car is approaching you in this way, you say the driver of the car is towards my left-hand side. But if you are standing on the other side of the road, then you observe the driver is on the right-hand side and the car is traveling in the opposite direction to what I had mentioned. So therefore, now it all changes with the different types of reference frames. I hope now you understood about what you mean by reference frame, and as a result of it, it's very difficult, it's very important for us to fix which one is the appropriate reference frame. Okay, thus what is a reference frame? Definition: a reference frame is a perspective from which we observe and measure position, velocity, and time, motion using a coordinate system. Very important is you need to fix a coordinate system for a given reference frame, and it's a set of coordinates to measure the position and time or the events, and this is what you call as a reference frame. Basically, there are two reference frames available. The first one is an inertial frame. An inertial frame is where the objects move at constant velocity or stay at rest, right? So this is called as an inertial frame until and unless there is a force which is being acted upon with it. Then the second one is a non-inertial frames, wherein the frames which involve acceleration or rotation. For example, if you are moving in a bus, what kind of frame is this? Is this an inertial frame or a non-inertial frame? It should be a non-inertial frame. Why? Because the bus starts from rest, then accelerates, goes to a certain extent, and then stops. Okay, so there's a change in the speed of the particle, speed of the bus over here. Right, now let us look at the inertial frame, some of the objects, some of the properties. So objects which moves at a constant velocity or remain at rest is called as an inertial frame, and no pseudo forces are being observed in that, and Newton's laws of motion always holds good into it. Okay, this is what you got as an inertial frame. Non-inertial frame. So objects move with a variable velocity or acceleration. So definitely it moves with a different velocity, and there will always be an acceleration over here. A circular frame of reference, a particle with an acceleration. All these are some of the examples. Pseudo forces in a moving frame is observed. You observe a pseudo force, right? Let me show you an animation based on this, like how does pseudo force applies, as you see over here. So a person is standing on a bus, and the bus is starting to moving over here. He is holding the handles over there, right? When he holds the handles over here, and as the bus starts moving forward, okay, as suppose if I apply a brake over here, when I apply a brake, what happens? I am just being pushed back forward over here. It is something like there's someone pushing me forward. Am I really being pushed by forward? I'm not being pushed by anybody else, but there is a pseudo force which has been applied, and this pseudo force makes me to go forward. Newton's laws of motion requires adjustments such that addition of pseudo forces are there to explain them. Okay, so it's not that Newton's laws of motion are not applied. It can be applied, but there should be some corrections which are need to be made. So you need to take up the pseudo force also into consideration. So let us look at the solutions for this. Which reference frames in this list are inertial frames? What do you think are inertial frames over here? A skydiver falling freely. When a skydiver falls freely, what will happen? He is under the influence of gravity. So definitely this is not an inertial frame. Then a skydiver falling at terminal velocity. What is terminal velocity? You already learned it. Terminal velocity is the velocity at which the particle is moving at a uniform speed, right? When there is a force which is acting downwards, there's a drag force acting upwards. Some of these two forces will cancel each other, and therefore, hence the particle moves at zero force. Net force is zero. So definitely this would be an inertial frame. A train moving at constant speed in a straight line. Constant speed in a straight line. Straight line means, okay, there's no change in velocity. Constant speed means definitely this could be an inertial frame. No external forces are acting in this case. A plane taking off. When a plane takes off, what happens? Initially, you see the speed of the plane will be zero, and after that, the speed starts increasing. There's an acceleration. So this is definitely a non-inertial frame. Motion of the earth around the sun. What happens? Motion of the earth around the sun. Theoretically, if you see that the motion of the earth around the sun is around 30 kilometers per second. Okay, it's moving faster and faster. It's rotating, okay, around a circular path. But if you look at the distance, if you look at the distance between the sun and the earth over here, this distance is much larger as compared to the speed at which it travels, or maybe the displacement that it travels in 1 second. So therefore, you practically consider that the motion of the earth around the sun is nearly an inertial frame. Okay, so therefore this could also be considered an inertial frame. Now let us move on to the next one. A student is cycling to school with her friend who is also cycling exactly in line. And as they cycle past a bus stop, they have to wave to their aunt who is stationary at the bus stop, and she waits for a bus. Okay, two students are moving. Okay, and then they wave to their aunt who is waiting for the buses. The student's aunt estimates the speed of students to be 5 meters per second. At what speed would the friend measure the student to be traveling? So how do you answer this? There's one student here. There's another student over here. And both of them are cycling exactly in the same line. And then as the cycle passes a bus stop, there's a wave to the aunt who is stationary at the bus as she waits for a bus. Okay, so her aunt is waiting at this point. Both of them, students' aunts, estimates the speed of the students to be 5 meters per second. So she estimates this one to be 5 meters per second. At what speed would the friend measure the student to be traveling? So both of them are moving at 5 meters per second. The friend would measure this friend, the other friend, to be moving at a speed of 0 meters per second, because he is also moving at 5 meters per second. He is also moving at 5 meters per second. The relative velocity between them is 0. Thus, the answer C is the right answer. Okay, let us move on to the next one. Okay, Galilean transformation. So far, we had learned about what are inertial frames, non-inertial frames, and how they are being linked to each other. We have learned all this over here. And now what we are going to do is we are going to take two frames which are moving with the same speed. That means we are going to take about inertial frames. And if the properties of one of the frames is known, how do you know the properties of the same particle in the other frame? That's what we are going to do. And that is what you are going to learn with the help of the transformation equations. What transformation can I use to switch between two reference frames? That's what I'm going to do. And this is what you call as a Galilean transformation equations. So towards it, a Galilean transformation equation is used to define or to switch between two reference frames moving at a constant speed relative to each other following the laws of classical physics. Okay, so that is what it's going to do. Now clearly, let us consider a frame like this. As you see here, this is your S is your stationary frame and S dash is your moving frame. And let us say there is an event. Event is nothing but a particle. Okay, let us say a particle is present over here, and this particle, now we are going to find out what is the coordinate of this particle. Now, how do I find the coordinate of the particle? See, clearly, with respect to this frame, with respect to stationary frame, this is the total distance x over here. This is the total distance x over here, right? So this distance, I show it to you here. This is the total distance x over here. And this should now be equal to this distance x dash plus this distance vt over here. Thus, I will be able to write x is equal to x dash plus vt. I can write like this over here. Okay. Now, if suppose, let me assume that this x dash, that is the coordinate of the particle, or the particle itself is now trying to move like this. Okay, it is trying to move like this. And let me assume the frame velocity is v and the particle's velocity is something like u over here. It's u over here. And now we are going to measure the velocity of this particle in the frame, in the S dash frame and as well as the S frame. Now, what is the speed of the particle in S dash frame? In S dash frame, the speed of the particle is u, which I have already defined. In the S frame, what is the speed of the particle? That's what we are going to ask. To get to know about this equation, what I do is I divide this by t on both the sides. When I divide this, I get x by t is equal to x dash by t plus v over here. Now, what is x by t? X by t is nothing but the speed of the particle, okay, this particle in the S frame. Let me call this as capital U. This should be equal to x dash by t. What is x dash by t? It is nothing but the speed of the particle in the S dash frame, which I have already defined over here, which is u plus what is v? V is nothing but the speed of the particle, speed of the moving frame, v over here. That's what we have done. We have just added the two velocities, right? We added the frame velocity and as well as the particle velocity. This is very similar to that of if a child is now moving, in the previous example we have seen, if a child is moving inside a train with a given velocity 2 meters per second and the train is moving at a speed of 15 meters per second, what is the total speed as observed by a stationary observer? This is a stationary observer and we have added these two velocities to get this. Right? So this is what we got as 17 meters per second in the previous example, and then we multiply this by 10 to get the value of 170 meters, which is the distance traveled. The same thing we have done. It is nothing but how do you transform the equations? Okay, how do you transform the coordinate spaces? Okay, how do you transform the primed coordinates to the normal coordinates? That is being done with the help of the Galilean transformations. Remember, Galilean transformation is applicable only in case of the inertial frames. That means the frames which are moving with a uniform speed as compared to this stationary frame. Okay. Okay. Now let us look at how the velocities can be manipulated or added in case of a Galilean transformation by clicking on this particular link. Now let me click this. Okay. Now let me share my screen to show you the animated screen over here. Let me go back to sharing. Right. My browser is opened. Right, I hope you can see this browser over here. Now this is a GeoGebra animation. I have put it to a full screen over here. Okay, I can run the animation here. There's a player button over here. The link is already there in the PPT. You can see that in the video also. So you'll be able to click on that. And if you want, I can also put the same link in my description in the YouTube. You can just look into it. Okay, now let me click on this. And before clicking, look at the parameters over here. What is this y here? Y is nothing but the y-axis. Y is equal to y dash, which means what? The moving frame and the stationary frame are having the same y-axis. It is not moving over here. And the x-axis, look at the x over here. This is your x and t plot over here. So you have an x here. So now this x will be increasing. See, this x is equal to x dash plus vt and u equal to u dash plus v. Now what I have done is there is a particle which is present over here, the black dot, okay, whose velocity is 0. Let me run this initially. When I run this, you see the x dash frame is moving, okay, with respect to a given velocity v, and there is an event which is happening here. It's a particle here, a black particle, which is stationary with respect to this frame over here. But according to this particle, this frame, definitely the particle is also moving along with it with the same velocity as that of the velocity of the frame. Now what I will do is I will increase this velocity. Okay, so you see the graphs over here, you have the graphs which is overlapping or it's aligning together. If I now increase it to, let us say I increase it to something like 0.5. 0.5. Now what do you observe? The particle in this frame, that is in the moving frame, has now started to move with a larger velocity, and as a result of it, you get a different graph over here, right? So you get a different graph over here. So you get this one blue color one shown here, and with respect to time, and thus you observe that the velocities are different. Now what is the velocity as observed from the stationary frame? The velocity would be this velocity v plus this u dash over here. V plus u dash is nothing but the speed of the particle as observed from the y frame. Okay. Now, so therefore, as time proceeds, this is going faster and faster. Right. Now, what I will do is I will make this one lesser and make it negative over here. Okay. I'll make it as something like minus 0.5. I make it minus 0.5. What's happening? The frame is moving forward while the particle is decelerated, or it's moving in the negative direction. Moving negative direction, so it is slower and slower over here, right? So that means according to this, now what could be the velocity here? If the particle is moving along the frame with the same, with a different velocity, positive velocity, then the velocities will get added up. Otherwise, it gets subtracted up. This is what we can understand from here. Okay, now let me come out of this and share with you my PPT to see like what does it, how do you proceed further. Okay, just a moment. Okay, now an inertial frame of reference S dash moves with pass with another inertial frame S moving to the right at speed S dash. Okay, we are talking about inertial frames moving to the right at speed 15 meter per second at time t equal to 0. The origins of the two frames coincide, which means what? This is your origin of your S frame and as well for the S dash frame is here. Okay, so S dash I will represent it by a different color. Let us say I'll take it as blue color. So this is my S dash over here. This is my S dash over here. Both the frames are coinciding at t equal to 0. Then a phone rings at location x equal to 20 meter and t equal to 5 seconds. At x equal to 20 meter. Where is x equal to 20 meter? This is x equal to 20 meter. At t equal to 2 since 5 seconds. Then determine using Galilean transformation the location of this event in the S dash frame. Now what is happening to the S dash frame? S dash frame is moving to the right with a speed of 15 meter per second. At t equal to 0, it was here. After 5 seconds, where will this be? This frame would have been moving like this. After 5 seconds, the S dash or X dash will now be equal to V into T, which will be equal to 15 multiplied by 5, which is equal to 75 meters, which means what? The phone is at 20 meters, but the frame could have been at this point, which is around 55 meters away from the phone. So what has been asked? Determine using Galilean transformations the location of this event. Which event? Which is the event here? The phone over here. What is the position of this phone with respect to the S dash frame? With respect to S dash frame, it is at a distance of, x dash is equal to minus 55 meters, because anything from here, this direction is positive, anything backward is negative. So this should be called as minus 55 meters. Then the next question. Then, okay, just a minute. Yeah. Ball is measured to have a velocity of 5 meters per second in the frame S dash. Calculate the velocity of the ball in the frame S. Now let us say, for example, in this moving frame, if there is a ball whose velocity is to be 5 meters per second. 5 meters per second. What is the velocity of the ball in the frame S? Now what should I do? I should now add the velocities, because you know, in this frame, the ball is now moving with a velocity of 5 meters per second. But the frame itself is moving with a velocity of 15 meters per second, right? So therefore, with respect to the stationary frame, maybe I should change my color of the pen. So with respect to the stationary frame, this is my stationary frame. What is the velocity here? The velocity here will be 15 plus 5, which will be equal to 20 meters per second. Thus the answer is 20 meters per second. Okay, I hope you understood about how do you use Galilean transformations over here. Now let us move on to the next one. Now the next problem says a ball rolls on the floor of a train at 2 meters per second towards the right with respect to the floor. So you have a train, which is moving, and then this is moving train at 2 meters per second. The train moves with respect to the ground. What is the velocity of the ball relative to the ground? To the right at 12 meter per second. If the train is moving at 12 meter per second, let me go back. If the train is moving at 12 meter per second and the ball inside the train is rolling at 2 meter per second, then what is the net velocity? Simple answer, v should be equal to 12 plus 2, which is 14 meter per second. Now if the train is moving at minus 12 meter per second to the left, which would be 12 meter per second, but the ball is still rolling like this over here, in that case what's the velocity? This should now be equal to 2 minus 12, which should now be equal to a minus 10 meter per second. Okay, now let us take up one more example. A train travels to a station at a constant velocity of 15 meter per second. One observer is standing inside the train, another sits on the platform. Okay, so there's one observer standing, one observer is sitting inside the train. Okay, he's sitting inside the train, and then another sits on the platform. Okay, there's one platform over here, another observer sitting over here, right? And as they pass to each other, they start the stopwatches and what is a child on the train run at a constant speed in the same direction as the motion of the train. There's a child which is running like this over here, okay, inside the train, right? At the same direction, the observer of the train measures the speed of child to be 2 meters per second. So he measures this one. Let me call this as V1 is equal to 2 meters per second. While according to the observer on the train, how far has the child moved after 10 seconds? According to the observer on the train, okay? So therefore, according to observer, what is the speed of the child? 2 meters per second. So distance moved by the child according to the observer on the train should be 2 meter per second multiplied by 10 seconds, which should be equal to 20 meter per second. 20 meters. 20 meters is the distance moved by the child due to the observer sitting on the train, due to the passenger sitting on the train. Okay, now let us read the next question. According to the observer on the platform, how far is the child moved? According to the observer on the platform. So what does the observer on the platform see? The observer on the platform will see the child is moving with 2 meter per second and the train is moving with 10 meter per second. I'm going to add both of them. So not 10, 15 meter per second. I'm going to add both of them. So which will now be equal to 17 meter per second. The child is really acing up like anything. It is going very, very fast. That's what the observer will see. And therefore, the distance moved by the child as seen by the observer sitting on the platform, who is not traveling on the train, it should now be equal to 17 multiplied by 10. What did I do? V into T. I use the same V into T. Remember, when you are talking about Galilean transformations, we are not going to use accelerations, okay? Because it only applies for constant velocity motions over here. So 17 into 10. So this answer should be 170 meters. I hope you got the same answer. So what is Galilean invariance? As you observe, just a moment, it's not been shared. Let me share it once again. Okay, Galilean invariance. What is Galilean invariance? Galilean invariance is a variance that is a principle that states the fundamental laws of physics, such as Newton's laws, are the same in all inertial frames of reference. Okay, so it means Newton's laws does not change when you are looking at a frame S or in frame S dash if it is moving at the same velocity. So Galilean transformations can be applied in such cases. Newton's laws of motion can also be applied. If you had applied Newton's laws of motion F equal to ma here, you will also be able to apply the same equation here also. Conservation laws are varied. How many conservation laws are there? You have conservation of momentum, conservation of energy, any kind of conservation laws are there. You can apply it over here. Velocities depends on the frame of reference. It only depends upon the frame of reference. Time and space are independent. Okay, very, very important thing. That's where now we have been looking at time and space are independent. Most of the time in our real life situations, we only look at time and space are independent. Okay, then next one. Galilean invariance works well at low velocities compared to the speed of light. Remember, this invariance works only with the low velocities and not with a very high velocity. Okay, when we go to higher speeds, we generally look at the relativistic invariances, which is nothing but Lorentzian transformation, which we'll be seeing in the next few slides. Okay, then, so Galilean transformation does not work out in these situations, wherein you see, okay, you have something like a set of stationary particles, positive charges over here, and you observe that there is a person who is moving across in a satellite or in a spacecraft. Okay, Jim, for example, shown here is moving at a spacecraft with a velocity v. Okay, so now you know from magnetism we already learned that when you are moving in a spacecraft, okay, initially when you have just static electric charge, it produces only electric charge, electric field. Okay, while if the electric charge just starts moving, then it also produces a magnetic field. Motion of an electric field, motion of an electric charge produces a magnetic field, right? So now in this case, you have a set of electric charges and you have another person, that is a person who is standing, who is sitting in a spacecraft, who is also trying to move. Okay, when it is moving, what does he see? He sees that the electric charges are moving backwards relative to him. Okay, when you say that the electric charges are moving backward relative to him, something like when you're moving in a bus or a car, you observe that the surroundings like trees, buildings, everything tries to move backward over here, right? In a similar way, charges also appear to be moving backward to him. When it starts moving backwards, that means what? A charge is in motion. When a charge is in motion, what will happen? It will produce a magnetic field. Now, what's happening here? According to a stationary observer, a charge only produces electric field. But for a moving observer, it produces an electric field and also a magnetic field. That means when he has a magnetic substance in hand, it will definitely grab across it, right? So this is what can happen. So therefore, your Galilean transformations here needs to be made some corrections. So in other words, it does not apply for things like electromagnetics. Okay, so that is where the next type of transformation comes, which is your relativistic transformations. So finally, we have come to an end to this particular video, which tells you about only about the Galilean transformations. And next we'll be studying about Lorentz transformations. So what we have learned, the key takeaways here are, you can see it is x equal to x dash plus vt, y equal to y dash, z equal to z dash, and t equal to t dash. And you can also see the velocities are additive, as you see here, ux dash is equal to either u plus v if the particle is moving in a straight line, or it's equal to u minus v if the particle is going backwards to the actual frame, right? While the velocities like y dash, y and z are unchanged because we consider the particles are moving only in a straight line. It's not that you should only consider this. You can also consider this in a two-dimensional or a three-dimensional motion also. But I am just putting across only for a one-dimensional motion. With this, we come to an end to the first part, which is Galilean transformation. Next, we'll look at the Lorentzian transformation. Thank you for being with me. Before leaving this, do share, like, and subscribe to my channel for more updates. So here afterwards, lot number of conceptual lectures and other things will be shown over here. Thank you very much.